Okay, so let's look at an example. Suppose I have this system, 1/5 dy by dt plus y equals cosine 5t for t greater than or equal to 0, and I have this initial condition that y of 0 is equal to 4. Now, this differential equation could have come about from a circuit, okay? And in particular, it could have come about from this, what I call RC circuit, where I have an input voltage source, I say A cosine omega t, where A cosine omega t could be 1 times cosine 5t, okay? Now, in this case, my output is the voltage across this capacitor, all right? So the voltage across that capacitor is going to be y of t. All right, now our process for solving this differential equation really follows in 3 steps. All right, we talked about this in class. First step is to solve the homogeneous equation, right, which is where we set the full differential equation equal to 0. So we remove the source. All right, we call that solution to that equation the transient response or the homogeneous response, or in the book they call that the complementary solution. We call it y sub c of t. Okay. Then what we do is we solve the non-homogeneous equation, which is the one with the source still there. The solution to that is called the particular or steady state solution. And the approach that's used always with that is what we call the method of undetermined coefficients, which means that we guess a solution, and that solution that we guess has some unknown parameters. So in the case of where we have a system where we have a sinusoidal or cosinusoidal input like this, we guess that the output is going to be a cosine with the same frequency. So cosine omega t plus phi, where omega is 5, right? What we say in this case is that we don't know what the amplitude b is, and we don't know what the phase shift phi is going to be, okay? This is our steady state solution. All right, so what we're saying is if I look at this top circuit, if I have cosine 5t as my input, I'm going to get some steady state output, which has got a different amplitude, but the same frequency and some phase shift from whatever the voltage is across the input, okay? All right, now, once we're done, we combine the transient or homogeneous solution with the particular solution to get our total solution. It's in this step where we figured out any remaining kind of unknown terms, all right? And there's always remaining unknown terms from the transient. All right, what we said in class is that if we guess b cosine omega t plus phi, which is correct and what is really happens in the real world, all right, that's a really messy approach. What we do instead is we say, well, we know that a cosine omega t is the real part of a e to the j omega t. Now, to remind ourselves of that, what I wrote out here is Euler's identity. A e to the j omega t is equal to this expression. All right, you guys should be pretty familiar with that at this point. Okay. All right, so we know this, and so what we say is, well, we could redraw this circuit as what's shown here in the middle, and we could say a cosine omega t is also the real part of a e to the j omega t. So in other words, if I did the voltage source here and the voltage source in this middle circuit, they're the same voltage source. Okay, that means that my output by the same argument, which I know is going to be b cosine omega t plus phi, and we're going to look at that in a real example here at the end of the video, right? I know this is going to be the case. So what that says is that I could just assume that the steady state answer is also the real part of b e to the j phi e to the j omega t. And again, you can look at Euler's identity to see that that makes sense. All right, well, because these two circuits are identical, what we sort of say is that, okay, we could just do our analysis using what we call the dynamic phasor, a e to the j omega t, which is going to, if we consider that to be our input, then what we're going to get across here for yp is going to be b e to the j phi e to the j omega t, like that, okay? And what we just need to do in the end is to take the real part of that result to get our answer. In other words, we can just perform our analysis entirely in the complex domain using this idea of the dynamic phasor. And then at the end, just take the real part of the result. Okay, and that's the approach we're going to take. All right, so let's do that. So we begin with step 1. which doesn't even deal with the transient response, or sorry, the steady state response. It deals with the transient. All right, so here we solve the homogeneous. Okay, so the homogeneous equation takes the original equation and sets it equal to 0. All right, in my mind, the way I think of that is the homogeneous equation is one without any sources. All right, so the source is removed. Essentially, this corresponds to a circuit that looks like this, if you think about it, right? It's as if I removed the cosine source from the circuit, and I'm basically looking at just the capacitor discharging, okay? So, in this case, we guess a solution of the form. We guess that y sub c, and again, the solution to that is y sub c, so I'm going to write it that way. Y sub c of t equal to c e to the st, where the constant c is not equal to 0. Okay, that's going to be the approach I'm going to take. All right, so I'm going to guess that as my response. And we talked in lecture about why that's a sort of a good guess. All right, exponentials always happen in these sorts of systems. Okay, so if I go in here and since it's a guess, I plug that in, d by dt of c e to the st plus c e to the st equal to 0. Then what I do is I need to take the derivative of the first term, so I get 1/5 s c e to the st plus c e to the st equal to 0. Okay? All right, at that point I see I've got some common terms here. C e to the st is in both of these terms. So it looks like I have c e to the st times 1/5 s plus 1 equal to 0, right? So 3 terms multiplying each other to equal 0. C is never 0 because we said we didn't allow that as a choice. E to the xt, exponential is never equal to 0. So the only thing in this expression that can force it to equal 0 is this term here, 1/5 s plus 1. So I know that 1/5 s plus 1 equals 0, or s equals -5. Okay? That means that our transient solution is c e to the -5t for t greater than or equal to 0. Okay? Now, the thing is, I don't know enough yet to figure out that constant. All right? That we need to figure out once we get to the last step, once we're looking at the total solution. So now we go to step 2. All right, so step 2, we find the particular or steady state solution. All right, the steady state solution tells me what happens once the transient is over with, okay? And we talked about the fact that we would have a b cosine omega t plus 5 for that before, right? So yp, we know, is going to be b cosine omega t plus phi, which in this case is b cosine 5t plus phi, okay? And the thing I want to do is I want to use the result we kind of discussed here previously, which is to say, if I go ahead and I convert my input cosine 5t to the phasor domain, and then I solve for the dynamic phasor for y sub p, then I take the real part of that, I will get back to this original guess, which is what happens in the real world, right? This guy is equal to the real part of b e to the j phi e to the j 5t. All right, so we're going to move over into that dynamic phasor domain, and we're going to say our input, so our original equation, let me write the original equation, dyp times 1/5 dt plus yp equals cosine 5t. That's in our real world. And then I'm going to say over here in our dynamic phasor domain, I have 1/5 dyp by dt plus yp equals e to the j 5t. At the end, I just take the real part of the result that I get, okay? So this is the guy I'm going to solve. Right, let's bring it over here. So I'm going to say my guess is going to be, in this case, b e to the j phi e to the j 5t, and of course I'm going to take the real part of that at the end. So I'm going to say I have 1/5, so 1/5 d by dt of b e to the j phi e to the j 5t plus b e to the j phi e to the j 5t, right? All I did was substitute in this result into this expression. That's got to be equal to e to the j 5t, like that. Now, I take the derivative here. So when I take the derivative, I have to be careful. B is a constant. E to the j phi is a constant. E to the j 5t depends on time. So that's the only thing I take the derivative of. That derivative is easy. I say I have 1/5 times j5 times, so that was by taking the derivative. The j5 comes down, right? So that's times b e to the j phi e to the j 5t plus b e to the j phi e to the j 5t equals e to the j 5t. Now this is the important part. I have an e to the j 5t in every term there. That just made a significant simplification, all right? There's now no longer any dependence on time, and that made this thing a heck of a lot easier to deal with. All right, let's group terms. We see we have a b e to the j phi in both terms here. So I'm going to factor that out. b e to the j phi. I have a 5 and a 5. They cancel each other. So it looks like this whole thing simplifies to b e to the j phi times j plus 1. If you multiply this thing out, you'll get the expression above. All of that equals 1. A significantly simpler expression. It's complex, but simple, okay? So what I have here, again, my point is I don't know b, I don't know phi, but I can solve and figure out both of them from this expression. So let's start first with the magnitude b, okay? So if I take the magnitude of both sides, b e to the j phi times j plus 1 equals the magnitude of 1. All right, now first of all, the magnitude of 1 we know is always 1, okay? b e to the j phi. So if I have three complex numbers, b e to the j phi and j plus 1, all multiplying each other, we know that when we multiply complex numbers, we multiply their magnitudes. So I have magnitude of b times magnitude of e to the j phi times magnitude of j plus 1, all equals 1, okay? So in looking at this, a couple of things. B is just a constant, so we'll say B is B. It's a constant real number. We know it's a constant real number because in the real world, we have a voltage that is B cosine omega t plus phi. There's no complex amplitude that you would have on a cosine, right? Now e to the j phi, if we're not sure, e to the j phi equals cosine phi plus j sine phi. So if you took the magnitude of that, right, the magnitude of e to the j phi would be square root of cosine squared plus sine squared. And you should know that cosine squared plus sine squared, all right, is always equal to 1. All right, so we know that that guy is 1. So b times 1. Now magnitude of j plus 1 is square root of 1 squared plus 1 squared equal to 1. So b equals 1 over the square root of 2. Okay, so we're done the magnitude. We go back to this expression. Now we got to do for the angle. All right, and so what we do is we say, let's take the angle of both sides. So the angle of b e to the j phi times j plus 1 equals the angle of the number 1. Now again, the angle of number 1 is obvious, it's 0. Now we know from complex numbers again, if I take the angle of a product, right, so I've got 3 complex numbers multiplied, the angle of a product is equal to the sum of the angles. So the angle of b plus the angle of e to the j phi is phi, and plus the angle of j plus 1, like that. Now, the angle of b is going to be 0 degrees because it's a constant. All right, so 0 degrees plus phi, and the angle of j plus 1 is arctan of imaginary 1 over real equal to 0. So phi is equal to minus arctan of 1, which, if you remember from trig, that basically corresponds to negative 45 degrees. Okay? All right, so we've determined that yp, all right, the complex phasor here, yp is, remember, real part of b e to the j phi, e to the j 5t. All right, so the real part of now apparently 1 over square root of 2 times e to the j negative 45 degrees times e to the j 5t, like that. All right, which, if, again, you go back to your Euler's identity, you should see that that's 1 over square root of 2 times cosine 5t minus 45 degrees, and I get that result. All right, that's our steady state solution. Okay, so now we need to go to step 3 up here, which is to find the total solution by combining these guys, and we use the initial conditions to figure out what any unknown remaining coefficients are. Okay, so let's do step 3. So step 3, all right, and I should, before I move on, this was a lot easier than the trig approach if I just plugged in b cosine omega t plus phi. That becomes very messy and there's a lot of trig identities. This approach here is a lot simpler, okay? Step 3, we do our total solution. All right, our total solution, which is y of t equal to y sub c plus y sub p. So that is c e to the negative 5t, that was our transient, plus our particular 1 over square root of 2 cosine 5t minus 45 degrees. Before I go too far, the one thing I want to point out, a transient we said always goes away, right? And we see that. It vanishes as t advances, c e to the negative 5t is going to disappear, and I'm going to be left with a pure cosine waveform. All right, and that cosine waveform, I notice, is shifted by 45 degrees from the original input, which was cosine 5t. Okay, so I need to figure out what c is. Now, up top, I had that the initial condition was that y of 0 was equal to 4. All right, so I plug that into y of t. So that gives me c e to the negative 0, right? C e to the 0 plus 1 over square root of 2 cosine of 0 minus 45 degrees. All right, so e to the 0 is always 1. So I have that c equals 4 minus 1 over square root of 2 cosine of negative 45 degrees, okay? Now, cosine of negative 45 degrees, if you look it up, what that is, that ends up being square root of 2 over 2, all right? So I get 4 minus 1 over square root of 2 times square root of 2 over 2. They cancel, and this guy becomes 3.5, okay? So therefore, our total solution, y of t, at the end of the day, is 3.5 e to the negative 5t plus 1 over square root of 2 cosine 5t minus 45 degrees. Now I want to take a look at this thing. This is our final answer, right? It's hard to just look at math without having any physical sense of what it means. And so what I'm going to do is I want to plot this. I want to use a circuit simulator tool called Simulink, which is built into MATLAB, okay? So in this case, one of the things I want to do is when I look at this, I got to think about how to plot it. All right, so when I think about it, the transient response I know is going to go away. And you should have seen that, you know, in circuits, they talk about the transient goes away usually for t greater than about 5 time constants, all right? And we know that in circuits, they say e to the negative t over tau. So looking at this thing, I have negative 5 equals negative 1 over tau. So it looks like my tau is equal to 1/5. So 5 tau is about, well, not even about, 5 tau is 1 second, okay? So what I wanted to do is look at this thing in a circuit simulator. All right, so here's the circuit simulator I'm using, okay? So what I did was I set up a sinusoidal source here. I have a resistor, capacitor, all right? The size of these components is such that it matches the circuit that we defined. And in this tool, what I have is this thing right here is a voltage measurement, measures the voltage between these 2 points. And then I'm also measuring here the voltage across this capacitor, okay, which is just like what I showed here, all right, for this circuit to model. All right, so the other thing I have here is a little oscilloscope, all right? That oscilloscope shows me what happens in this circuit, okay? So let's run this. All right, so it ran. I look at the output on the oscilloscope, okay? And what I see here is my, in the yellow, all right, this is the input, all right? So this is cosine 5t. So this guy looks like cosine at t equal to 0. He starts high and just varies. And he's labeled up here in the legend as the input voltage. The blue is my output voltage. This is y of t, okay? And we see that it starts at 4, just as we said that it would because we gave it the right initial condition. Here we see the transient response. We said it should be done in you know, about a second or so, 5 time constants. Looks like it is. By about a second or so, it looks like our transient response is more or less dead, and we're left in steady state, as we'll be, if we leave this thing turned on forever, we'll be in steady state for a long time. And what we see is that y, the blue, the output, is basically just a cosine waveform, all right? It's a cosine waveform that's a little bit smaller than the input, okay? And phase shifted a little bit, okay? That's maybe the real kind of key takeaway from looking at this is that when I go to my solution, what we see is that once the transient response is dead, what we're saying is that the output is basically also a cosine with the same frequency, but its amplitude is a little bit different and its phase is shifted. So let's validate what we got out of the circuit simulator, right? This guy says that once we get to steady state, right, what we should have happening in steady state is that the amplitude of the output should be 1 over square root of 2. 1 over square root of 2 is about 0.7, okay? And if we, so let's look at that first before I talk about the phase, all right? So where is my scope? okay? So to measure the output, what I'm using is this thing here called cursors, which is the way you take measurements on an oscilloscope. And when I do this, I have two cursors. So number 2 is this dashed line. I've lined that up with the peak here of the input. And then my output Y, I've lined up number 1 here, the solid line, with the peak value of the output. All right, so over here in this little window here, it tells me that at cursor number 1, the time where cursor number 1 is this value, and the value that it sees is this. So what it says is that on the blue waveform right here, which is my output at number 1, right, the value that it's reading here off of that waveform is 0.701. And that is, in fact, pretty much what we predicted. All right, pretty close. Now, it also says that the angle should be negative 45 degrees. Now, how do we validate that? Because in the real world, when we take a measurement of this waveform, right, our axis here is in time, right? The real world is measured out in time, not angle, right? So how do I actually verify what that angle shift is? Well, it's the measurement of the shift between the original waveform and what I got at my output, okay? So in other words, the distance between these two lines here, the distance from the peak of the input to the peak of the output, that should be 45 degrees. Now, how do I check that? Well, what I can do is, in the real world, again, I measure the time difference. So the time between cursor 2, the peak of the input, and cursor 1, the peak of the output, says it's 156.429 milliseconds. Okay, and I can convert that to angle because I know that omega t is always an angle. Okay, so what I'll do here is I'll say omega delta t equals a delta angle. Okay, and so our omega is 5. Our delta t was, I think I said 156.429 milliseconds. And that's going to be an angle in radians, right? Because this is radians per second. So I'm going to convert that to degrees. I like degrees better. So I multiply by 180 degrees over pi radians. If you do that math, you see that that works out to be about 44.9 degrees. All right. And so the key thing here is it's also negative. All right, why negative? Right, the reason why it's negative is it relates to the relative shift between the input and the output. All right, so in other words, to get this input shifted over to where the output is, I'd have to move the input to the right. All right, and a shift to the right is a negative shift. All right, a shift to the left is a positive shift. So if I had to shift this guy over to the right, that's negative 45 degrees. All right, so hopefully that helps a little bit to understand what's going on.